we go. So thanks everybody for coming this evening as we end the 5th year of the Silicon Valley Automotive Open Source Group. We will be starting our 6th year next month with a meeting on Saturday, October 1st at the Stanford Cars Center, where we will have a presentation and little mini lab tour of the Stanford Solar Cars project. That event is strictly limited at 30 because that's how many people the facility can hold. And last I checked, we were at about 20 already. So if you're interested in going to see the Stanford Solar Cars project, please go ahead and sign up for that. Then November 7th at Fujifilm in Santa Clara, Tom Coughlin, who's head of the Flash Memory Summit and an authority on data storage technologies, will be giving a talk about the use of data storage in cars. And in addition, Fujifilm is going to mount some demos for us to see before and after the talk of their heads-up display technology. So that's November 7th in Santa Clara, and registration for that event is now open. I'm hoping we're going to have an event about Skytran, the overhead monorail. Well, it's not a monorail, but the overhead lightweight transportation rail system in December, which has a potential tour out at Moffett Field. That would be cool, but we'll see. But just mention also on Thursday night this week at Peloton Technology in Mountain View, there is an SAE, what is it called, Innovation Group Meetup, something like that. If you look at meetup.com, the meetup group that SAE has, they're having 3 speakers on Thursday night in Mountain View on general connected car topics, by which I mean I can't remember exactly what they're talking about, but I'm sure it will be great. All of you are here this evening, I know, to hear Ricardo's presentation. Does anyone else have any announcements about job openings, events, product releases, books for sale, any topics that they want to promote before we get started? No? Well, in that case, I'll turn the floor over to my soon-to-be fellow MIT alumnus, Ricardo, who is going to give us a talk on a very timely topic about which much has been assumed and little has been measured until now, I think. So thanks very much, Ricardo.
Yeah. Thank you. Thanks for letting me take up your evening for today. Let me plug this in. All the material I'm going to be covering is wide open and available to you guys. So this is actually a slides.com deck that you're looking at. I just ask you that you don't follow it while I'm looking at it because it would be kind of weird. But there's, and it's very deeply linked into the resources that I'm going to talk about. So I really came here to share. My little bit about myself. Oops, laptop's locked. Hold on. Yeah, so I am actually got 2 lives going on. I am an MIT Systems Design and Management Program 13. That's my cohort. It's actually our website a couple weeks back, and that's me over there. And anybody else from the cohort here? No, invited them. I didn't see them yet. But it's a really interesting program where you have to look at very complex systems and define requirements that are related to safety, project management. And the great thing about the program is it actually allows you to have a life afterwards, so you can do it part-time. And as a result, I've also been able to work at Amazon during this time. And I have most of my time at Amazon has been with AWS. So I've been with Amazon for about 3 years. And I basically bootstrapped the Boston office, and that's where I'm from, by the way, and got the folks really thinking about cloud computing. Cloud computing, and not only in the context of replacing data centers, but really leveraging and offloading some of the heavy-duty work that typically is done either locally and moving that over to the cloud. What's been keeping me busy now, that's my daughter, by the way. It's the Alexa. So how many of you own an Echo? Yeah, I have a bunch of them, as you can tell. It's a really fascinating technology. It has nothing to do with cars, not yet, but it's really fascinating to see voice being embraced in different platforms. So my day job is to really get Alexa's voice to be in many devices, cars included. But my main motivation here is actually it's safety. I mean, it comes down to safety. I'll show a video here. This is actually, I modified, I put a time code on this video. And this is in seconds, in frames. So you see here that we had an incident on this road. And it's, you know, we talk about vehicle-to-cloud latency. And we can sit here and watch this. It's actually a pretty painful video to watch, but it will take a long time before this accident actually stops, right? So my motivation really is to maybe not save the first 3 or 4 accidents here, but the other 40 that happen within the first 60 seconds. I think it's totally within scope. And it's funny that the commercial driver actually knows what the hell is going on, and he is driving slow. But there are folks that really, this takes them by surprise. And I think that we can do a better job, given that everybody's got the internet in their pocket nowadays, that we can do a better job in saving some lives here. This is actually not a remote event. A lot of this happens. Now this is, I'm not sure exactly, but I know that in, a second, having a hard time. I know that in 2013, it was actually a pretty bad year for this. There was an average of two pileups per week in 2013. And a pileup is defined by USA Today here as a crash of at least 10 vehicles, or 5 if somebody was killed in it. So this is actually a very common use case. You guys probably experienced this when it rains in California, right? And you know the oil comes up and the road becomes super slippery. So this is really my motivation. It's safety. And I think it's a use case that we can actually reach with the technology readiness of today. I was also inspired by a feasibility study that I read as part of my research for my thesis. The CoCar team it's actually it's a German, it's a European study that did feasibility of cellular hazard warning systems. They're actually using broadcasting of cellular towers to be able to communicate safety events that may be happening ahead of you. And they were doing some filtering and broadcasting using their data centers, but leveraging this 3G technology to deliver what basically is a safety use case, telling people that there's a big problem ahead fast enough so that they can do something about it, right? And this safety use case can't read German, but you can see here, this is actually pretty much what we built. What we're going to be talking about more today is the situation where if there is a hazard, or there's a construction, or some event that's detectable on the lead vehicle, that we can transmit that over to the cloud using 3G networking, and then and then broadcast it over to relevant cars. What's fascinating is their conclusions. Back in 2009, right, they basically said you can do this today, right? And you actually get safety gains. There's actually this feasibility document looks at a lot of aspects: financial, market, technology, of course. And in 2009, these guys declared that this is actually doable, right? And they're actually looking forward towards LTE because even more use cases will be more doable. So I think it's about time somebody really takes a second look at this and starts to enable some of these use cases. Now, the DOT is actually not waiting around. They are trying to homogenize all these different ideas into applications that will work across state lines, right? And they've done a great work with building out, basically collecting a lot of the academic material around reference applications. So if you go over to the Iteris site, you can actually see 60 or so reference architectures with links over to the academic papers that were talked about. And a lot of them do address safety. This is my favorite. It's actually related to the video that you saw. This is the spot weather impact warning system. Just kind of walk through this here. This is the physical view of the architecture. Again, this is publicly available information that the DOT put together for us. And what it does, it allows drivers who are in control of the vehicle to get information that's coming from the intelligent traffic system equipment and the traffic information centers. And that data is actually being gathered from probably the most reliable sensor that's out there in the road today. That's the car, right? It's at the right level of where the weather issues might be happening. And this deals with having onboard equipment in the vehicle that's reporting either via roadside equipment or directly via cell network over to the Traffic Information Center. Traffic Information Center figures out what reports are worthy of rebroadcasting and sends it out to road message signs, the variable message signs that you see on the road, or to vehicles' dashboards, those vehicles that are connected. So this is actually a reference architecture that is being worked on and improved on. There's several updates that the DOT is really maintaining this fairly well. Encourage you to take a look at it. Another development is the head unit aspect of it. Any folks from Ford here at the Palo Alto office? If you are, I was going to hug you because I really like the work that you guys do. Specifically around the Ford Sync, it's an amazing platform, right? The Ford Sync has been open sourced into Smart Device Link, and it's a great way to actually get data from the head unit. You don't want to go on the OBD port, right? We all know that. And you get data in a safe way from the head unit, and then the best way too to also interact with drivers. You can have alerts, text-to-speech alerts, things that show up in the dashboard, and allow the driver to interact. Because frankly, the last thing in the use case that we're talking about that you want to do is to distract the driver when he's doing 70 miles an hour in treacherous conditions. You don't want to do that. You want to use the HMI. But at the same time, you want to develop things quickly. So if you can install a library in Android or iOS, you can start building applications that will run, that will get vehicle data, if Ford gives you the permission, and do something about it, and also display itself on the head unit. This is great. Actually, Ford has a lot of hackathons on this. And the first time we played with this, Rimchi is actually on the, he's here. Raise your hand. Here he is. That's our first hacker. So on Tech Disrupt, in Disrupt SFO last year, we met and we got this idea. It's like, hey, what happens if you get not just one head unit, but get two head units, and make him talk using a very low latency protocol called MQTT. It was brilliant. It was fascinating that how quickly it worked in the world's crappiest Wi-Fi network, which every hackathon has, right? So even in a super saturated network, we're able to get head units to respond to each other in a very quick way. But it was a nice, we're using, I think at the time, the IoT.eclipse.org server, it kind of worked. It was sufficient to get us free tickets to the rest of the conference, which was pretty cool. Yeah. So I took this on to, kind of to the next level. So as I mentioned, I work with AWS, and just 2 weeks after that demo in the TechCrunch, we launched a service called IoT. So the AWS IoT service was launched October of last year. And I want to just kind of quickly go through a little primer of what this service means. It's not magic. It's really MQTT in the back end, right? MQTT as a protocol is a beautiful protocol, very lightweight. It allows things to be permanently connected, subscribe to topics. And the topics are, we did some interesting things with the way we structure topics, and I think you're going to enjoy the simplicity on it. But it's fast, it's good, it's low power, which we don't care too much about in a vehicle, but it's nice to know that it's a lightweight protocol. And what IoT does, it basically puts a broker out there for you, right? It allows you to, and it does it the AWS way, super scalable, very reliable, highly available. And it allows you to basically go from 1 to 1 billion subscribers without having to worry about, toppling over the little Eclipse test server, right? And it's secure. By default, you have to have a cert in order to talk to the service. There's rules that are associated with the the actual device itself. We can decommission them. If they go rogue, somebody takes over a device, you can just take it out of rotation so it doesn't impact your IoT pipeline. So we did our connected car vehicle using this service, but a really magical service that also uses the rules engine. So the rules engine allows you to actually inspect the messages that are coming through the broker and do something about it, right? So, and you can call other AWS service. You can also send it on the message back. So what I did with that feature requires a knowledge of geohashing, which I'm sure you all have, but just as a review, it's a really beautiful way to reference a location, because you can be, depending on the number of digits that you offer, right, you can get very specific, right? So if you just do a 1-digit geohash, it's basically 1/4 of the world, the flattened world, right? But if you do something like 6, 7 digits, it can get pretty specific. So if you can emit a message with a geohash code, and somebody listens to one that is, everybody that is subscribed to that geohash pattern or shallower is going to get that message. So there's this concept of wildcards in MQTT. So basically, following the example here, if I subscribe to sensor/hash, and I send a message to sensor/temp, that subscriber is going to get that message, right? So this concept of wildcard is really important, because what I did with it was actually really simple, right? I created this concept of a topic tiles, right? So I created I would emit messages under certain geohash, and then things that cared about that would subscribe to that topic, right? And as the vehicle moves along, it subscribes to the new topic. So as the car is moving, as the head unit is changing its GPS location, it changes its subscription. And I actually vetted this with our engineering team at AWS. Said, guys, is it okay for me to do this? Because I'm going to be talking in a conference and people do this at scale. It's like, sure, yeah, we can handle that. That's no problem. Having something subscribe a bunch of times like that as it moves, not an issue, right? So we took this idea of, you guys understand the idea? Is there any questions on what yeah, Ricardo. All vehicles. I was presenting, there were 400 people in the conference in my session alone. Yeah, I presented the number of miles of roadways in the United States, cars traveling. It was, they basically laughed at me. It's like, that's not an issue. Yeah, we built it for much noisier things than that. Cars don't travel that fast, apparently. Yeah. Advertising is always bigger. If we spent, I'm sorry, this is being recorded. The amount of effort we do to do things on the ad space, we could probably solve many other issues. But any other questions about the technical approach that I took here to subscribe as we go along? Yeah. Yeah, so as you move out, the logic on the POC is pretty simple, right? Once you subscribe to one and it's successful, you unsubscribe to the previous. But you could think about making this more intelligent, right? By the way, I'm not trying to replace any amazing routing mapping API here, but this is like 2 lines of JavaScript in the rules engine, and we got it to work in a very lightweight way. There's no massive numbers of JIS servers doing this. It is 2 lines of something in a rules engine that makes this work. But you could think about, there might be a smarter way to subscribe this, right? Because the more specific a subscription is, the less false alerts you get, right? It makes no sense for you to subscribe to something that is behind you. So understanding the vehicle heading would be a nice improvement to this logic. But it's very simple subscription logic. Yes?
You just answered. I was going to say, if you were altering the geocell topology, you formed that in the shape of a roadway in the travel of the vehicle.
No, this is strictly geohash. It's still a grid, and it's still can be incorrect sometimes, especially in northern latitudes. Very simple geohash, but it's like a couple lines of code, and it's brilliant how it works. Yeah. No, geohash it's strictly a grid. It will change. I mean, if you move 20 meters this way and you have a precise enough geohash, you're going to have a different number, one that looks very similar to the one that you had before. There are libraries, very simple libraries that we can convert a lat long into a geohash. Yeah, it's just it's simple, but it does require dexing on Android, but that's not news. But it does, in Android or iOS, you can say, hey, here's my lat long. I need a new geohash for this. And then that's the topic you subscribe to. Once that's successful, you drop the previous. Very simple logic.
Why is it even necessary? Why isn't GPS enough?
We care about topics of where we're heading. Because GPS is not a very good way to structure DMQTT topics. Right? I need a way to be able to have a number that I can structure into deep topics. Because I may have, for example, if I'm a car that's driving very fast, I may subscribe to a larger square, a larger grid than a car that is stopped in traffic. That way I don't get weird warnings if I'm stopped in traffic. But if I'm doing 75, I have a little more headroom. Right? But the challenge here is not geohash versus GPS. It's how to come up with a nice, elegant way to subscribe to a topic that represents a grid. And a lat long is not really, you can't really make a topic out of that. Okay? Is its depth. Yeah.
Based on your topic.
In the hack that we put together, no. But it could say, hey, I'm going to subscribe to a deeper, I'm going to create a more precise geohash out of my lat long if I'm moving faster. Or I'm sorry, if I'm moving slower. Yeah, flipped, sorry. Yeah. So that's the concept between, very basic MQTT topics has been around for 25 years, and geohashes probably been around even longer. And, well, not the libraries, but the concept probably. So we took the service. And so if you're looking for an AWS architecture diagram, this is it. I mean, we're starting from your left. You have the lead vehicles and the lead and also sensors that might be on the roadway that is ahead of you. The car and the follow vehicles are on your right. And what you have is the AWS IoT services that are ingesting the events, deciding whether or not they're worthy of republishing, of rebroadcasting, and when they rebroadcast, these cars or these road signs are subscribed to it. Okay? So if you're interested in actually seeing this live, you could, it's really weird to use a computer that is being remotely controlled by this. Okay. All right. Yeah, so I'll try to speed this up here, but okay. Yeah, we're not going to stay for 40 minutes, but this is me with shorter hair. So you have 3 emulators. The emulators are all subscribed. They all are running. Let me just pause for a little bit here. So you have the emulators are the AppLink emulator, and it's okay. What I'm explaining here. So the emulator is, it represents a head unit that's running Forward Sync. And then there's, of course, a mobile app that's associated with it. It's the mobile app that's connected over to the IoT service, right? You see here that, once you plug the phone in or enable Bluetooth, it connects, and then the application eventually goes away. And because you're not really supposed to be looking at your phone while driving. It's just a background application. So that's one application. And what I did for the demo is let me see if this works. Did 3 of them, right? And of course, I used a bunch of AWS services to ingest the data. Somebody asked about Elasticsearch, Kibana. Where is that guy? There you are, Taka. That's Kibana right there, ingesting all the vehicle events. But then you actually put them on a map, and this is the interesting part. What I do is I enable a safety event on the lead vehicle. As soon as I enable it, I just throw it in park, which is the only thing I could do in this head unit emulator. As soon as I do that, it's hard to see here, but one of these guys are going to look like they're, okay, I'm going to do it right there. Pay attention to the road sign. Okay, so I threw it in park. The map will show that it crashed right there. And then this is the road sign, which is a little Raspberry Pi to subscribe to the same topic. It also showed. And what the cool thing is that these cars still are not, they could have been notified, but we chose not to notify them because they're not subscribed to a bubble that's big enough, right? They don't care about the accident that's 20 miles down the road. But eventually, when they get to it, the head unit shows the, yep, just about, there you go, that one lit up. And then the next one is also going to light up, right? So this actually was really good demo. Really lucky because these emulators were running on a virtual machine, and Android emulators on a virtual machine in front of 500 people. It's, I was really pushing it, but it was a good day. I got some good feedback. Some folks came up. I love people that come up after a demo and say, hey, good stuff, but you know what? You're full of it. First of all, I saw a bunch of VINs on your Elasticsearch demo. That's not going to fly. Don't show VINs and speed limit on Elasticsearch. Don't do that in a demo, okay? Just heads up for you guys. So privacy was a big deal. And of course, running things on an emulator, it's always fun. Then I got together with the STL guys, and at CES, they had a real vehicle that I could play with. So we did it in the car as well. This is pretty cool. This time I had an iOS version of the message sign. There it is, right? So that's subscribed to a topic. The interesting part of this video, I'll fast forward here, but it's, so that's obviously the car, and it has the application running. And then I have a virtual car on my lap, which is the emulator on my laptop. So I'm going to switch over to that in just a second. So that's a virtual car that's next to this car, right? So I set the GPS so that it's also close to it. And what happens is, as soon as I set the virtual car to the safety event, both the message sign and the head unit will light up. But this is the cool part, and I don't know how to do volume here. There isn't volume. But the cool part that you'll see here is when I do the opposite. What I did is I treated braking, stepping on the brakes, as the safety event. And when I step on the brakes of this vehicle, the laptop emulator car immediately lights up, right? So what you see here is that this stuff works on real cars, first of all. We had to change very little. The challenges that we had in going from the emulator over to the head unit, first of all, we had to port no code because it's still running on a phone. But the types of vehicle data patterns or available vehicle data from cars kind of changed a little bit. Okay, here's the part. You see my foot on the brake right there? 1, 2, 3, hit the brake. All right. So you can kind of see it right away as soon as I hit the brake. And the sign lights up as well. So there was very little porting to do. I had to just do a better job handling error codes because sometimes the vehicle data was not available because the GPS units were different, and then the app would not behave as well. Question?
Yeah, I just want to. So when you're stepping on the brake, you're publishing an MQTT event with a geocode to it?
I'm saying yes. In my rules engine, so I'm publishing a very specific, the vehicle data, the entire vehicle data that's available from the head unit. I'm sending that over as an MQTT message, and then I have the rules engine inspecting the brake on part of the payload. And that's the thing that will emit back to anybody that's subscribed. And the sign and the laptop will subscribe to the specific hash code where this car was.
So I, as a client car, subscribe to braking information.
Yeah, but yes, you just have to give me a little creative liberty here because this is a POC, right? Stepping on the brakes, it's the only vehicle data that I could emulate without asking for it to recompile stuff, right? What I really want is it didn't give to me. I wanted the ABS stuff. I actually wanted the ABS actuation. And they thought about it. They're thinking about it, mostly due to the trouble that we caused at TechCrunch.
Accelerometer in your phone.
Yeah, I know. But, phones fall down. I want the real stuff. And it's there. It's like somebody just needs to be able to bridge because there's a nice protective layer between what's going on in the CAN bus and what's published over to the head unit. The frequencies are also different. The head unit only does 1 hertz. The CAN bus is doing things much faster than that. So, but that would have been the best data set to get. Okay? Yeah. Great question. This is actually the CES Wi-Fi. So it's probably much worse than LTE. But it's still, and you just asked, you gave me some feedback, How about latency? All right. So, which is why we're here. Sorry for that long intro, but I think you guys would need to know, where I came from as far as what sort of use case I was trying to solve for. So, field test, road trip, right? People asked about latency, and I was curious about latency. I never had issues with latency where I live in Cambridge, right? You just have to make sure and see. If you're at MIT, you got to use T-Mobile. No, AT&T. And if you go to Harvard, you got to use T-Mobile. So latency is not a problem. It's amazing, though, that even in an urban center, you have issues with cell phone providers, especially in older towns that don't like cell phone towers, right? So it's definitely a problem. And the whole simple proof of concept that I built relied on a proper network connection. So I decided to go do some testing, okay? I already had the tooling that would do the proof of concept. Now I needed a different tooling that would just get me the right data. So I chose a very open test approach, right? I'm really here today to kind of hand it off to you guys, right? And it's something that uses open source tools to capture the data. Anybody can do these tests, right? And I chose a pretty interesting route. More details on that in just a bit. And also the results are open. You guys can have all that data and do something cool with it. Hopefully add more to it, okay? It's a heck of a lot of data points. The tooling is the FCC speed test. How many of you have seen an open source tool that has 4 stars and over 1,500 reviews? That is fascinating, okay? Not only is it fascinating, by the way, you can if you look at one of the forks, Sim Knows is the contractor that built this for the FCC. Really cool guys in the UK. I forked their stuff to very simple changes. I wanted to control my own endpoints that I was testing. I didn't want to hit their CDN. I wanted to hit my cloud, or my cloud, different clouds that I provided. And also I enabled the continuous mode of the app, which runs the whole time. Their app that you download from the App Store is much nicer to your bandwidth. It runs like every couple hours or something like that. But it's wide open. You can actually look at the fork that I did and see what I did to it. The tests, so there are several tests that the application would do. You can select them. The one that I chose is UDP latency and packet loss, right? I didn't do download and upload because that would have been a problem with my data plan. And not so useful either, because sometimes it would have taken so long to do a download that I actually would have had less resolution on my testing. So I just stick to the basics, UDP. Plus, with download and upload, then you have to ask, well, how about the back end? Is that you saturating that? UDP kept it really simple. The tests, as documented in fcc.gov, this is really important, guys. I made sure that the methodology and the code is openly documented, right? They send a UDP packet that's essentially time-coded, and they count how many they get back, and then they inspect the time that they came back, and they give you a round time. Yes?
But MQTT is
Good point. So I couldn't find an open source tool that had that many stars that was MQTT. These are different things, right? So you're right, I'm not testing MQTT, but I'm testing the network. So I'm taking some liberties here, okay? But I think you can validate the differences very quickly in a lab environment. You don't have to necessarily travel. You can probably duplicate, But you're right that there are different protocols. But this is the protocol of the tooling that I had. A good point. Okay. So you can see here, we're going to talk about these latency numbers in very detail today. So you can take a look at what is this test doing. I bought a bunch of phones. So I was actually specific about the phone because I needed to get the same piece of hardware that will run CDMA and and the AT&T and T-Mobile frequencies, right? I did this a lot of times, guys, about 102 times. But so this T-Mobile, AT&T, Project Fi, which at the time was, it's really interesting. Project Fi has changed. When I tested it, I thought I was using Sprint, T-Mobile, and US Cellular. A message from Google saying, hey, US Cellular is now enabled. So actually, I think my test, it's hard for me to tell based on the data, they don't disclose it, that I was actually only hitting the Sprint and T-Mobile towers when I was using Project Fi. It's a very interesting service, and we're going to focus in the quality of in their results, which I think are really fascinating. But it's right here. It's the Nexus 5X. I actually still have a couple of these phones around. And same piece of hardware with 4 different providers, including Verizon, which gave these phones a really hard time. Cloud, of course. I was very, I picked every single available region as of June 2016. I was really mad at Google because they enabled the Dales, Oregon data center for Google Compute 4 days after I drove by it. So that's to say that these cloud providers they're really growing. They're like bunnies replicating data centers everywhere, right? So this is actually an outdated list, and I know for sure the AWS side we already pre-announced a couple more regions there. So watch out, Azure. We're going to catch up with you. At least they're everywhere, which helped them in this test. But I used all the U.S. The larger regions. I didn't pick every single region. There was some gov things, but if they were in the same location, I just picked the bigger one that we can run a lot of compute. On the cloud instances themselves, I was running Red Hat Enterprise Linux. I was consistent about that, even though it cost me more money. By the way, 90% of the license of the hourly cost goes to Red Hat. Okay, so these providers can actually be a lot cheaper if you go to CentOS. But the binary that I had from Semnose that was doing the back end was built for Red Hat, so I chose that. I chose the smallest instances available. Okay, and these have burstable networks, but I did monitor the network. I don't have the data, unfortunately, but it didn't blip. I mean, the types of loads that we're doing from these clients was not even showing up on the reports for these instances. And I had to pick a route, right? So I did this route on an electric car. So I had to be very specific about what to follow. This is actually a time series map. You can see here that I took 5 days off in my trip, right? And then I picked up my wife in Kansas City, and then we did the full loop and saw some amazing places, but with absolutely no time to stop because I had to get back to work. So we just plowed along and using the beauty of autopilot, got my data safely. Actually, the trip was split into 3. It was an eastern loop, northeastern loop, west loop, and a southeast loop. My co-pilot for the west loop was my wife. She actually composed the whole piece. It's going to be played in the Boston Opera on November 15th. There's actually a link for that on the notes. So that's how bored she was. But the worst part about this experience is that she was composing, so I couldn't blast music. It was like a very mellow time by myself. For this, the Eastern Loop, my dad joined me. This is his favorite road. Do anybody know what this is? Where this is? No, it's more south than that. It's actually Louisiana. It's 18-mile long bridge. Actually, probably 2 weeks ago, this was totally flooded where my dad is here. We're about 5 miles west of it was in Louisiana. That's where that was. Baton Rouge, 5 miles west of Baton Rouge. Yeah, he loved this bridge. He's a topographer. I think that's how you say it in English. So for him, straight roads is like amazing. So he loved it. Okay, let me see if there's any. Okay, that's the cool stuff. So let's jump into the results. As I mentioned, the results are open. You guys can go into carto.com and pull this stuff up. I'm going to kind of navigate you through it so that you know what you're looking at. Okay, so first of all, the test coverage. I think it's important to know when were my phones on, right? Because one thing that it's important to note about the results is that if you don't see a data point, it means nothing. It could mean that the service was probably really good, I just didn't capture it. It could also mean that it was so bad, I failed to capture it, okay? So to show you the distinction, so these are all the points where my phone, all phones were on. And I was actually pretty good about turning these things on, okay? You can see here that, even through Utah, even after Vegas, I did a pretty good job in keeping my phones on. I didn't do a very good job in Napa Valley. So I did forget to turn my, actually no, that's a different location. So there were a couple gaps in my data. I just forgot it. I was not drinking, but I just did not remember to turn all the phones on. I was looking at the beautiful places there. So you can see here all these places that the phones are on. Now, but I did have 5 data providers with us, right? So let me enable them one by one. You can kind of see how good these are. I'm going to first enable AT&T. So what you see here is an overlay of AT&T, and it will show, regardless of its performance, green if you had a successful test. Okay, so you see that it's actually pretty damn good, right? I can see why Tesla chose AT&T for the U.S. For their infotainment stuff and their telemetry. It was probably the most reliable performer. But it has its issues. I think even and when you see green here, we start zooming in, because nobody, if you start to see that things, there are some gaps, right? I mean, even in Grand Junction here, you start to see some gaps here. So there are places where it fails, right? There are places where it's successful, right? So by the way, you could argue that maybe there was just bad logic running, a bad phone, or maybe it was just having a really hard time, right? So if I zoom in here, I have this, right? It's a challenging place. But you see here that at a national scale, right? If I was a guy looking for I didn't care that much about latency. I had a reliable enough code, and I just wanted a global coverage out of a single provider that I can negotiate my, out of. This is not a bad choice, right? Ricardo, what's up?
Question about indicating on this map here, or on this graphic. So green indicates that you had a connection, or green indicates that you had some kind of latency test?
No, green indicates, and this is all documented in the logic, if a packet does not come back within 3 seconds, it's declared a failure. Yeah, so it's basically above 3 seconds, right? But it's a failure. It could also mean I just forgot to turn the phone on. It could also mean the phone ran out of power. That's this right here, right? It basically means the phone had issues. They could be service issues. They could have been hardware issues, okay? But I want it to be, full disclosure, when you look at the AT&T data set, it's successful hits only. And that's the one you want to focus on, because failures don't mean much here, because it could be just bad ways of getting the data. Yes?
And again, this is UDP ping, maintaining a DTP.
Correct. Yeah, that's all. Yeah, UDP pinging, as simple as it gets on the network side. Yeah. I might go back next summer. I don't know, and do more. Let's look at this. There's more than just AT&T. I showed you kind of the best. Let's now focus on Project Phi, which is a really interesting one. All right. So pretty good in the Northeast. Oh, that's not right. Okay, let's do T-Mobile. Project Phi was a lot spottier than that. Something's going on. That's why. Okay, sorry. That's all. Yeah. Thanks, guys. Okay, let's go back to Project Phi. Yeah, there's Project Phi's coverage, right? So you can see here that it's a lot less spotty, a lot more spotty than AT&T, right? So these are areas where their virtual mobile operator couldn't even find anything to grab onto, right? But you see on another map that I'll show you in just a second that it has other performance characteristics that are outstanding from a performance perspective. So it's the coverage versus speed dilemma that we'll see, and you can't tell that from this graph, but it is pretty interesting. I want to show you some problems that I had with this test as well. You guys finding this interesting, this approach to looking at the data? Okay, hopefully. Verizon. I'm sorry, Verizon. I had a really hard time with your phone. This is not indicative of the network. Again, it's the testing. Okay, on full disclosure here. I had some issues with this phone. It would just not lock on to a Verizon tower. the car moves so much. It's really weird. Like there came a point where I had to reset the phone several times in order for it to grab onto a tower. Really odd. If there's a Verizon engineer here, please let me know what I did wrong. But I had some issues with the stability of the Verizon service on the 5X, the Nexus 5X phone, and I think this is the part that I really struggled with. Now, I do want to highlight the all. I forgot to talk about that one, and I want to ask you guys a question. So I was supposed to take the 101 north in California. I was just going to be the engineer, because I really wanted cloud latency to be low. My wife said, we better go see the Pacific Coast Highway, okay? And this is what happened. Every single provider failed here. Blackout. All my 4 phones became heaters. What's going on in this area? It's Big Sur.
Castle and Big Sur, yeah, there's nothing out there.
There's nothing out there?
You're the mountains, the ocean, you're on this side of the mountain.
Yeah. I definitely felt that. It was beautiful. But
Focus on driving.
yeah, you do. Otherwise, you hit the construction workers there. So it was fascinating to see this big of a gap, 20 miles from the most high-tech place on the planet, which actually tested my theory, right? My theory was, I think we can do this. And then I picked a road and where all phones just went dead. I mean, nowhere, guys, not even in the middle of Montana was it that bad, okay? So California scores the lowest points for coverage in my route. But that just speaks to the fact that you have to have software that's robust enough to handle situations like that, right? So there you go. That's what I get for driving the Pacific Coast Highway. And she said, you can always go back and do the 101 later. I'm like, no, it's not the same. Okay, what else do I want to show you here? I think that's all for now. That is coverage. However, there's more interesting bits. Okay, cloud region differences. So as a solution architect for AWS, people see that we have 3 regions, and they're like, oh, I want to use 3 regions because I need high availability or low latency. I'm like, oh, hold your horses. Look what you're walking into here. Is there really a difference? That what you're seeing here, there's actually a difference. I was very surprised to see this because I just did a direct line distance and laws of physics and light speed. I'm like, oh, it's going to be at most 10 milliseconds difference or 70 milliseconds difference. It's not. It's actually much higher than that when you take in all the different hops and different things that you need to do to get to the data center. So this is the vehicle to cloud latency when you're hitting the AWS. I'm sorry. Let me just make sure I have the right thing here. When you're hitting not just AWS East, US East, but also GCE East, which is in South Carolina, and Azure East, which is somewhere in Virginia as well. So what does this mean? This means that you actually start getting some decent latencies. Now in this case here, right around here, 76 milliseconds. I don't. I'm just using the wrong computer. Sorry. Right around here, Verizon, 100 milliseconds, right? When I hit AWS East, if I hover a little more, 73 milliseconds when I hit AWS US East from the Phi network. Phi network to Azure East, even in Denver, is still giving you 93 milliseconds. Pretty good. Denver's the I-70 corridor is really well connected. T-Mobile, not bad. 120 milliseconds over to Azure East, which is all the way here. But you see that if you're shooting for 100 millisecond latency on your design, and you just use the East data centers, you're not going to cut it. It's going to be really hard for you to achieve those latencies, right? Let me see what else I'm going to talk about. So it does matter. Let's switch now to West regions. Kind of flipping the... Okay, I'm not sure if the projector is doing a good job there, but you can see now that it's not better, right? If you're using... And by the way, this does not include the new region for Google that they launched 4 days after I drove by it. The AWS US East 1, which is in San Francisco, West 1 in San Francisco, West 2 is in Oregon, and also Azure West 1, which is somewhere in California. They just say California. But you can see here that you see some green on the West Coast, and that's expected because you're closer to the data centers. Yes?
For your application, though, jitter is more important than raw latency.
Possibly, yeah.
Definitely.
Yeah, actually, one of the things that I did capture was packet drops. So that's something that is in the data. You can actually look at how the number of packets that came back. So I can actually, maybe offline, we can dive into that data and see where the worst drop was. Yeah. By the way, my purpose, in addition to sharing the data set here with you, is to get more interesting ways to look at this data. And so that's good feedback there.
But presumably the cars in the snow care about latency too. One of those cars coming at that pile up in the snow, 100 milliseconds difference is a long time.
Well, we saw 56 seconds go by and accidents were still happening. So I'd argue that,
Sure, you
yeah.
still stop most of them even if it was a full
Right. Yeah, I think 5 seconds. If I set this to 5 seconds, it's going to be green everywhere, except for the places where I turn off the phone.
Why I ask is TCP underneath you is going to go into congestive backoff.
That's right.
Because of the round trip time calculation.
Yep.
It's going to introduce false delay.
Right. That's a good point. I mean, UDP is the simplest test here, but I do capture, that same test does capture the packet loss. So that's a data set that you do have access to. You don't have to drive to get that. Okay. But it's fascinating too, and I want to show you the difference between Central and WAN. So look at Central for a bit. So Central is a bunch of data centers from Azure. They love the Central. They have Chicago. Basically it's called Central, North Central, Central, and South Central. They have 3 data centers, 3 regions, and AWS doesn't have one yet. Google does have a Central region. But you can see here that it's sort of the best of both worlds, right? It's still, you get some green on the east, but you're still dealing with a lot of challenges here. I think the challenges here, I know the challenges here aren't really due to the data center locations. It's the phones. It's the mobile networks to get to the cloud. Okay, so there's hope. You start to see some green on this graph, right? And you notice that choosing the right region may make a difference. So when you're working with your cloud architect, let them know what you're trying to do with the cloud service, right? Because sometimes it matters, sometimes it doesn't. Keep in mind that I was actually hitting a region. I was not hitting a POP, a point of presence, right? AWS has got like 10 of them in the US, but you can't run compute on them. So my little UDP servers, I actually had to run in a real region. That's why I only had 3 of them for AWS. Okay, how am I doing with time? 8. Okay, no, keep going. Got some good stuff here. That flashed too quickly. Low latency corridors. Yes, I coined that. They exist. There's a lot of them. Yeah. These are dots that came back round trip time in less than 100 milliseconds. And by the way, so you can hover over here and see the data. So AT&T came back in 77 milliseconds here from Azure North Central, for example, right? So you see here that, let me see what I'm looking at. So all the central regions are delivering this. Let me switch over to the east regions. Okay. So if you do use all regions and all phones, this is what the possible map of the United States look like under 100 milliseconds, right? Now, of course, things look good when you look at this altitude from space. But as you dive in, you start to see some gaps in the coverage, right? You don't get that lovely solid curve. I mean, somebody here has to worry in Glenwood Springs, right? There's a gap here. But you see that there are instances of fairly low latency that exists throughout the U.S. in existing networks, in existing cloud providers. The big question comes in is, what is the scope of your app, right? Because what you're looking at here is every single cloud provider, every single region that they offer, and every single phone. That's possible, probably, but it's going to be an expensive commercial application, right? So you have to kind of pick a region of where you plan to operate under very low latency and pick a provider that meets those requirements. But the good news here that I have to share, and maybe it was obvious to you guys, but they do exist. And they're, especially in the eastern half of the US, it's pretty reliably present. Now, There are some known issues. I touched up on them a little bit, right? The phone stability that I had of Verizon. So my Verizon data set is probably a lot worse than it should be, okay? Yes, my dad knocked the power supply on my AT&T phone. The good news is that I had to stop every 2 hours, so at most I would lose 160 miles of data, right? So I wouldn't go like for 600 miles not knowing that there was a problem. Timeout retries, basically they are timeout logic in the app that if it fails, it will just, I think there's a certain number of failures that it will tolerate and then it will just shut off. So there were times when I passed a bad region, but the phone stayed off. Again, the data sets that you're looking at are actually probably worse than they should be. I didn't have the time to, it's tricky to write logic that defeats that because then you have, you can actually have a situation where the phone is doing too much work and interrupting its own test. Plus, it requires a lot of coding, and Ramcha knows how well I code. And I did have issues with Google Compute Engine instance, but again, I just picked one very small instance. I'm not surprised that I had an issue, but because a proper architecture would have used multiple machines, I should know better. I'm an architect, right? But I was paying the bills, so I didn't build a highly available instance everywhere. But again, this is just saying that the data set is actually worse than it should be. There's also some unknowns. I only traveled once on my route. I was actually very specific about that, except that I visited Topeka 4 times, because that's where the center of the 8 was. I visited a supercharger 4 times. It's funny. But I'd never experienced, for example, the same network at different times of the day. So, for example, I hit rush hour all of the East Coast, but mostly in DC. I specifically remember going through there, bazillion cars near me, just like you guys have here every day. So for sure, the network speed is different when you have more demands for it. And I think a proper study will probably take a smaller route and just drive at different times of the day to figure out how that matters. If you're down to the millisecond difference, you need to look at time of the day as well. A very cheesy summary, okay, that I have here is, as of June 6, 2016, if you're looking at latency numbers that are around a second, you can pretty much have a single provider, single mobile network provider, and a single cloud region. For example, Project Fi on Google Compute, right? Or AT&T on Microsoft or AWS. Pick one region, pick a big one where things are cheaper. And a mobile provider that supports your location, and you're good to go. No need to worry about buying everything on every region. However, if you start to push the limit, then you have to start looking at multi-cloud solutions and multi-network operator solutions. Okay? So that's my results. I'll pause here, see if there's any questions for you guys. So how are we doing with timing?
Probably need to wrap up sometime in the next
Okay, half hour. Good. Perfect. Yeah. So let me ask you guys a question. What I just showed you, is that sufficient to go out and start declaring that you can build low latency safety related applications for vehicles? Cities have different issues actually. So much for the GPS assumptions. It's really, I just looked at 2 little components of a very complex system, right? So it's time I put my MIT hat back on, because I was just a guy wanting to drive a nice car around the country with a phone turned on, right? It's great that you get the data set, you get to dig into it. It was an amazing experience, but the reality is there's a lot more to build safety-related things. It's nice to see that there's hope for, good networks. The folks from the CoCar project, in 2009 said it's going to be better. I just proved to you that it is already better, right? But there's a lot more to this, and I want to take a kind of a back-to-school moment here and look at some of systems thinking that needs to be done around these topics, because I think it's pretty important. I'll try to do my best on this, but I think it's important that we look into it. So at school, at MIT, system safety is a pretty big deal, and it's some of the professors. And Professor Levison took a couple courses with her. Pretty amazing professor, and really a leader in looking at safety from a safety perspective, from a culture perspective. Okay, so she has a couple of things, a lot of publications, of course, and there's a systems theoretic analysis model that is being done to analyze complex systems. Because if you actually look at connected cars with drivers driving the vehicle, and many drivers driving together, it's a social technical problem that we have, right? So you can't just look at failure modes. I can't go say, hey, I got 93% of the dots that I retrieved were under 100 milliseconds. That means it's going to work 93% of the time. It doesn't work that way, right? You have to look at the accidents more as a chain of events, right? In very dynamic processes, right? You can't really treat the accidents as failure modes. You can, but in complex systems, you're not going to do very well. And any time you use software that's developed by humans, you're going to have interpretation of requirements. And the bad software is going to run perfectly 100% of the time, right? So you have to approach this in a different way. The STEP model approaches the accidents as a control problem, not a failure problem, right? The whole idea is to enforce a set of constraint that allows for safety to emerge from that system, right? That's what STAMP really forces you to kind of understand. With STAMP, you can analyze either a future design or a previous design using different techniques. I'll go into that in just a minute. And look at component failures, interactions across components. If the head unit is telling you something, if the dynamic message sign is telling you something else, how do you interact? Which one do you trust, right? You can look at human and software behavior and catch design errors earlier in the game. It all comes down to just a basic control loop, right? So you need to look at your very complex box diagram and do something that they really drill on you on the systems engineering programs is how to make it simpler, how to get complexity out of it so you can actually see the details of the problem, right? So you decompose the problem down to essentially a controller. We have a process model that is the controller is using to do control actions through actuators, controlling a process, getting some data out of it, and feeding back more information to the controller. If you do this with this connected vehicle problem, you might end up with something like this. Why is it? Well, at its core essence, there's the components, the things that run in the car, and then the things that run in the cloud, the technical pieces, right? But surrounding that, you have operations layer. You even have, all the way up to government and rules and regulations. There's somebody from the DOT here. He knows what I'm talking about. There's regulations that drive, the impact and the performance of the overall system. So if you really want to see how safe your thing is, you got to look at the full picture, right? So this is quite important, and STAMP gives you a chance to do that. It gives you a scalable approach to look at the full picture, okay? So back to STAMP, it's this idea of a controller. You have a process model that the controller uses to do the actions, right? I'm driving down the road. I have a process model of what the road capabilities are, the vehicle capabilities, the speed, the separation. Those are things that are in my head, right? And that I keep in my head, and that feeds me information so I can act on it. But I still get into accidents. Why is it? Because sometimes I do stupid things, right? I give the car unsafe commands, right? I give the car commands that are too late or too early, right? Or I just forget to give it safety commands altogether. So there's 4 different hazardous control actions that you look for when you analyze the safety of a system using STAMP. Okay.
I would suggest there's a 5th point. With the network here, you've got intrinsic latency.
Oh, yeah.
Which means you've got oscillations, positive over control.
Absolutely. Yeah. What you're seeing here is a super simplified controller diagram. The thing that you have, I'll show you. I have an exercise for the reader slide, which is not even that complex. It's basically different controllers impacting the behavior of other controllers. Right, so yeah, and there's classical examples, for example, in automotive systems like the auto start interacting with the hold mechanism, and if you don't do things correctly there, you have the car fighting each other. You have unsafe conditions, right? So there's 2 ways to use STAMP. One is sort of forward-looking; it's early on in the design, And the other one is, oops, something happened. Let's use the same systems theory to figure out what actually broke down, what constraint was violated so that we can hopefully patch it and avoid repeating the same error. So this is just a little flavor. There's a lot more that Nancy has put together, including workshops. If you want to go to Boston in the spring to learn more about STPA and STAMP, they actually have workshops, and you have leaders from the in the safety engineering side of various companies that get together, and it's really cool to see a space guy and an automotive team and somebody that's responsible for like nuclear radiation type of machinery coming together and doing analysis on using this approach. So I do want to kind of give you a little flavor for what the approach looks like. My best take at it, hopefully. Let me see if I'm done with this section. Yes. Okay, so the stamp process is why am I showing you this? Because all I've solved so far in this last hour or so, I said that there's a chance, right, that latency numbers meet the requirements. But it's a much larger picture. So we have to actually look at a higher level and go through STAMP and figure out STPA and go figure out what are some additional requirements. Because I only found 2 really interesting ones to measure, but there's a whole lot more, right? So the exercise involves actually starting with looking at potential accidents and hazards out of the system, right? Looking at the control structure, brainstorming what some unsafe things that the controllers can do, and figuring out what are some of the causal factors that are result from those unsafe control actions. And that feeds more requirements into the system. So very quickly, if you look at the road hazard warning system, right, potential accidents that could come out of that at a very high level, it can have a vehicle collision, right? A car can collide with a fixed obstacle. It's, those are accidents or losses that you can have. There's an interesting one that you could argue is a mission loss, the inability to complete a mission. So if you're doing STPA, for example, for the delivery of a satellite to orbit, right? If you don't get that satellite in orbit, that's an accident. That's a loss. If it blows up on the pad, it's even worse, right? But that's a loss, and you need to consider, what is the mission of a vehicle? I would argue that getting to somewhere on time could potentially be, or missing that window could potentially be considered an accident. There are hazards, things that we are under control in your design that can cause those accidents. For example, not maintaining a separation distance between the vehicles. If you violate that, it can lead to an accident or loss under tougher conditions, and so on. So it's important to define those because the requirements that you're going to derive from this need to point to the accidents and the hazards. This will support your requirements. This is the fun part, is the control structure, right? And this is actually hard when you're dealing with a very large complex system. You have to boil things down, right? So boil down the connected vehicle applications to basically 3 elements, right? The traffic information center, think of this as the control towers of the future for cars, right? The cars themselves and drivers, which may still be driving, right? The control structure, then you build a set of feedback loops around it. So you could argue that the traffic information center is posting speeds, perhaps through variable signs, and the drivers are hopefully looking at those, okay, and executing the maneuver. Maybe they're speeding up or they're slowing down to match the speeds. The car is giving feedback to the driver, but it's also, in a connected vehicle scenario, giving feedback over to the TIC, right? So this is one example of a control structure. What we're going to do here, we're going to zoom in. So we look at the driver and the car and actually break it up a little more, decompose the diagram a little more into the actuators, right? And then we're going to brainstorm a little on some of the possible control actions. So what can a driver do in a car? Well, he can steer, he can brake, he can accelerate, keeping things pretty simple here, right? And he can also configure the vehicle. He also has a process model in his head of when he should be doing those things. So you document those things, right? Good brainstorming exercise. It keeps the problem focused. And then you try to break it. This is the most interesting part of STPA, is the definition of the unsafe control actions that are possible in that very simple system that you defined. Okay? So you look at one of the control actions, such as reducing speed, and you define what happens if you don't provide that fast enough, or if you provide it too slowly, if you provide it for too long, right? There may be situations where if you, for example, reducing speed is provided, there could actually be a problem when you slow down traffic, right? If I ask everybody in California to do 20 miles an hour, you're going to be in the road the whole day, right? So you need to look at the problem in both ways. A couple more things. Then you define safety constraints that are related to those unsafe control actions. So, for example, if you to avoid a hazard, you have to, for example, provide warnings within a certain distance of the roadway segment that has the issue. And this is the most important part. Once you have those safety constraints in mind, you go back and you figure out what are some of the issues within your control sequence that may be violating those safety constraints. I'll give you just some hints here. For example, feedback delays, the whole topic of this presentation, right? Could be an issue. But you could also have an inconsistent process model. Maybe the process model that you're capturing is missing some information, okay? But your job as a safety engineer is to look at the causal factors that may be resulting in those unsafe control actions, which open up hazards, which could potentially cause losses, right? So this is a pretty deep exercise, and it allows you to identify some pretty interesting things that you may not have been aware of if you're just focusing on latency. The whole purpose of the second half of the section here is to open up your mind and saying that, hey, it's more than just latency. You got to look at the full system, right? And you need to now, once you know what the potential causal factors are, you need to go back to your control stack and say, what is it that I'm missing, right? Am I missing something in my process model? So I need some audience participation now. Why do you think people speed? Get there sooner. Okay, save time. But as you know, and my wife made me do this on the supercharger, we did this test in Montana. Doing 80 miles an hour with us adding more time to my full overall destination because I had to charge for longer. So the ideal speed to drive a Tesla in the summer in Montana is actually 65 miles an hour, which means every single truck is terrifying you because they're doing 80, right? So it's actually not necessarily true, especially with the electric cars. But yes, to get the feeling, right, of getting there sooner. But some of the things that we're missing, like we know what the law says, right? We think we know how to drive, but the car doesn't tell us what the maximum speed that it can handle. So we're missing that part of the process model, right? And the funny thing is that the car knows it. Right? If I put, auto steer and autopilot on at a certain speed and it starts to corner, it will actually slow down because it knows that speed is too much for that corner, right? So some vehicles, not all vehicles, know what its limits are, but that's not being reported back to the driver. So there's a missing piece of the process model here that I believe, right, if we start providing that information to drivers, say, hey, this is the maximum speed that this vehicle, given the current conditions, is able to handle. How do we know that? Well, maybe through machine learning or through some better sensor logic locally. I think we're going to start making some better decisions, right? Just another example. Another thing that you might be missing here, right, is the feedback loop. I drew, so there's two different control diagrams here. We know today that we don't tell the transportation center anything. This is the reality of today, right? We don't report anything. If we do, maybe the cops do if they stop me or something, but there's maybe through road infrastructure. Sorry, there are sensors on the road, so they probably know more than I think. Okay, but without that feedback loop, how can the traffic information center properly report the speeds, right? It's like there's something missing here. But if we can go back to our control and say, hey, there's a leg here that's missing, we should probably report locations and the vehicle and invocations of the ABS or stability control to the tick so they can send real-time warnings that people will actually pay attention to and obey, right? But without this feedback loop here, which is basically what connected vehicles give you, right? It's impossible to achieve that design. Yeah.
Looked at the results from the safety pilot program, for example, or the big study that was run in Germany. They were pilot studies of connected roadways. Do you have any comment?
I haven't looked as deeply as I mean, I'm aware of them. They tend to be, older studies but I don't know.
The most recent one,
Yeah.
a couple years old.
Right. Yeah, I don't have any. Is anybody familiar with the details of that study?
The basic safety message of
Right.
period right now.
Okay.
So you're still getting that long vehicle kinematics.
Yeah. So the basic, there's we could talk about what's the best payload to report that protects privacy and gives useful information. The basic safety message, I'm not even sure if there's actually there's a standard already approved for that, but other way.
Standards that you want to know about.
Okay. Yeah. That would be interesting to learn more about that. Yeah. My point here is that by looking at a different way of analyzing the safety of a problem, we start to identify some big gaps, some process model gaps that really impact how people drive their vehicle, and some feedback loops that really make some of the data that you see on the road signs sometimes irrelevant, right? And so you take the learning and you actually come up with your requirements, and your safety requirements will drive more information, more desire to build something better, to analyze it. I want to give you just an exercise for the reader here. Do I have it? Yeah, here it is. Yeah. You can't see it. So this is actually two control systems, okay? You have the driver that is trying to control the vehicle motion. Yeah, I'm sorry, wrong mouse. The driver is one controller, right? And then you have the TIC, the Traffic Information Center, is the second controller. So the Traffic Information Center is getting, weather service data. It's getting directives from the Traffic Management Center and roadside equipment data as well. But ultimately, it's actuating the messages on the variable message signs, and for connected vehicles, sending head unit notifications. So that's its goal. That's what it's controlling, is the frequency and content of those messages. The driver has as data input for its controls those messages, as well as road input and what the vehicle is giving. And that's the one that's he's the one that's responsible for actuating the speed, changing the speed and the direction of the vehicle. So you have a very interesting controller scenario here, right? So you can see that this problem you need a scalable way to analyze this. Try doing, using a different approach to analyze the safety here. It's just really, really difficult. And as I mentioned, there are some more examples, much deeper into real life systems that are even more complex than, not more complex than connected vehicles. That's pretty complex. But ones that will they've done safety analysis, cast analysis of systems that have resulted in personal injury and in the health care space, and also many other examples. So in summary, let's peel back, right? A lot of text here, but low latency use cases requiring low latency are feasible. I basically copy and pasted the 2009 results onto this bullet. Okay, they're even more feasible now. But there are these low latency corridors which have a potential to support even more demanding applications. Very appealing. But there are still latency gaps. You can mitigate them. You can mitigate them with virtual mobile operators, for example, multiple providers or multiple cloud providers, but they still exist, right? And they add even more complexity to automotive control systems. As you guys can see, you need a better approach to analyze the safety of such systems. Just declaring we have low latency because Ricardo said so is not going to make it any safer. You have to look at the full picture and its impact. Okay, that's it. Questions? penetration, having it's being behind a 20-year-old pickup or cars that don't necessarily implement that. I don't see an issue of it. It's just different ways to solve the problem.
Would still, in your scenario, also be an obstacle that.
Yeah, I mean, I don't see any issues of it. I think what I'm proposing here is something that can be built today and deployed and running in pretty much everybody's cell phone, right? For example, or something that's a little more, in the vehicle itself that will eventually be ubiquitous. But I'm not here to say, LTE versus, the radios in the vehicle. It's just that it is very compelling to use existing technology that is that good and that widely available. Think about the amount of developers that you can throw at this problem, right? That already know the platform. It's we can get some solutions really quickly here. Yep.
Japanese did their connected vehicle program in the thousands, where they started did a lot of tests around the platform. A lot of the particular where the humans had the most problems with the solutions, are also the ones that caused the most problems with the intersection, a blind intersection where you had a building right on the corner, block line aside from the human, but it also caused wireless signals.
Right.
And their solution ended up being, the only way they found out it would work is take a better spectrum. So they went to megahertz, which is a very expensive spectrum, but that was how they were able to broadcast through buildings.
Sure.
But doing kind of like general availability, but thought about where are the areas where I have the most access? How do I focus on problems exist and what is the coverage?
Yeah, I think you mentioned that the urban areas are a challenge for sure. I think the urban areas do benefit from having better infrastructure. You can actually have, for example, cameras in those locations that could report the presence of people that are in that crosswalk, for example. So you might be able to leverage something that is outside of the vehicle. But I don't have any specific comments on that.
They did do that with
But I just want to make it clear, guys. You've seen my expertise to the extent that you've seen it. So this is just a question for the group, okay? All right.
I think it's called ITS Spot or Spot ITS, but what they said is we're going to pick the worst areas in terms of accidents, and we're just going to put there because it's also some other.
It makes sense. I mean, I think when you start, and I hope I happen to work for one of those companies. When you see something that's like magical and very consistent, there's usually a lot of hard work behind it. And sometimes that hard work is very, just saying we're going to focus on this and put manual things until something else gets better, right? So that's definitely one way to solve the problem is to throw horsepower on it.
Yeah, apropos his point, I'm just wondering why we have a focus on RF signaling when we've got modulated LEDs and taillights, audio signaling, low level, high frequency or low frequency. I mean, we can modulate an LED on the roof of every car today, and that gets around our RF problem with buildings on corners.
Right.
In front of you, or snowy conditions. I'm just wondering why we have this fixation on RF.
Red communication was part of the are using it for something in terms of RF and interference for but where the problem was non-line the other vehicle because there's a
I'm wondering why we don't combine these things.
like they did study both of them in their ITS program does.
Second question was totally different. Have we learned anything from like Waze about these kinds of systems? Slower feedback, but it is kind of this control system.
Yeah.
What have we learned from that?
I mean, that's a good question. It's not something that's so open. They used to be more open before they were acquired, but it's fascinating. It is the default system that a lot of folks use, but there's still that 5 or so minute latency, right? Or a human entering data. I'm very surprised that they haven't, especially with the ability to get data from head units using the mobile application, that they haven't gone that extra mile to get information, at least from the accelerometers or get the human out of the loop from reporting. They could be so close to it. I'm not sure if you guys are more connected to them, but they are, head unit enabling their application to get data, for example, out of AppLink would make that essentially a hands-free unit that gives you real-time data. Yeah.
Yeah. So I was also thinking if you consider like the topology of the mobile networks, because basically, I mean, the tower is where the tower is, and sometimes if you're doing a handover or something like that, you might get worse things, but like there might be even better or worse times.
That was definitely not part of the study, but one of the things that I'm not sure, like given the protocols that we're leveraging, I think the CoCar example was leveraging lower level protocols that Ericsson did the study, right? So they could probably do things at a lower level with cross tower communication to pick the right time. But at the layer that I was working at, I was very well removed from it, and thus relying on their ability to do the right thing. Okay. Yep. I captured that. So on the data set that you guys all have access to, you can see exactly what radio, and even though it was a T-Mobile provider, there's also a SIM card operator, so you can see who was really giving you the service and what type of radio they were using. So that's part of the data set. Yeah. It just says, I think I took that out of there, but the name is still there. Yeah. If any of you look at the data and say, this looks too clean based on what I got out of the phone from the FCC app, let me know. I can give you the actual raw source pre-cleanup. That's not actually, I will just post that. But the way that app stores the JSON is very fragmented. You have to do joins and a bunch of other stuff, so it's a little bit harder. Yeah. Yeah, that's what the original, the CoCar study was using those technologies.
That's why I asked you, because that was a very interesting picture. And if just that could be enabled.
It's just not something that a developer can get access to. That requires more intimate, mobile operator. Yeah, and they can work at a much lower level protocol that's more efficient for sure. Yeah, take a look at that study. I linked to it in the notes, and you see that they were working much deeper on a stack. Yeah. Unfortunately, the study is a little older, but it's still somewhat relevant.
Questions for Ricardo?
I hope you guys enjoyed it. You can get all the data from slides.com/ardematos. I'll post it to the meetup as a comment. And I'd love to get your feedback on it and see where we can go with this. Thanks so much.
Hand me lapel too. Or no, there's lapel one. Yeah.
Like connectivity is much more important, because then your stuff you do is going to be the thing you